Okay. All right, let's start with this real quick. Depletion region, you put a p-type and an n-type material together. This is an example of the n-type and the p-type material. The electrons diffuse from high to low concentration, so they move in this direction. The holes do the same. So when the electron gets over to the p side, it recombines. When the holes diffuse over to the n side, and they also recombine. And what's left in the middle is the depletion region. And the depletion region consists of immobile ions. This is an example of the column 5 dopant, arsenic or phosphorus. Has a +1 charge associated with it, and this has a -1 charge. So the electric field is set up in the depletion region, going from right to left. All right, now what we're going to do today in class is talk about the electrostatics of the depletion region. How much electric field is generated? How much space charge do we have? How much voltage do we get? This electric field is actually what generates that 0.7 volts that's typically associated with the diode. All right, so this is an important aspect of physics. So let's jump ahead here. All right, equilibrium behavior of the depletion region. So what we've established thus far is that there is a depletion region in the middle here, where there are positive charges, positive immobile charges on the n side, and then negative charges in the depletion region on the p side. So xn0 here is the location of the edge of the depletion region on the n side, and negative xp0 is the location of the edge of the depletion region on the p side. This 0, this represents x equals 0. So this is the interface between the p and the n materials. So the electric field, I already mentioned to you before, it goes in this right to left direction. Does anyone remember what these regions are called? This is the depletion region. Yeah, these outside regions are called neutral regions. Why are they called neutral?
Recombination happens in this.
Recombination happens, right? But there's a specific reason why it's called neutral.
There's no net charge.
No net charge, exactly. That's a key point, because in the middle, where there is net charge creates electric field. So there is a strong electric field in the depletion region. There's no real electric field on the p and n regions. There can be if you put a voltage on those two ends. Like when you connect the diode to a circuit, there can be some electric field there. But by and large, the strongest electric field in the diode happens here, right in the middle. All right, so when we're trying to understand that electric field, we have to first look at charge density. There's a high level of charge density on high positive charge density on the right side of the junction, negative charge density on the left side of the junction. And in this particular example, you see that the charge density is higher on the right side, on the n side, than it is on the p side. So what does this tell you about doping?
Higher concentration on the n.
There's a higher doping density on the n side, right? Higher doping density, that means there's a higher concentration of those ions. So that's why that has a higher charge density here. All this charge density is coming from those dopant ions. So there's a higher charge density here, so higher doping concentration here. This is actually equal to Q times Nd. Nd is the doping density. On this side, notice that it's not as tall, but it's wider. So this is not as tall. Why is it more wide on this side of the junction?
Depletion area is greater.
Depletion areas is greater, right?
Because we need to keep the same number of charges on the positive and the negative.
Yes, that's the key point, right? The right side has higher charge density and it has a certain diffusion length associated with, not diffusion length, depletion width associated with it. This side has to have the same number of negative charges. The number of positive charges that you see here has to equal the number of negative charges on this side. So the side that has high doping density, those positive charges are packed very closely together because there's a high concentration of dopant ions. On the left side of the junction, the negative charges, remember there has to be equal number of negative charges and positive charges, those negative charges are more spread out, so that's why the depletion width on the left side is longer. The way that you can express this, like this charge equality, is by basically saying that this area that you see here, the area of this box where my mouse is right now, is equal to the area of this box here. So a box that's tall, it has to be narrow. A box that's shorter, it needs to be wider. So that's what both of these have the same total area. Okay. Now the next step is looking at the electric field. So we're actually trying to get more quantitative on this. Now, the value of charge density here is Q times ND. So we know Q and we know ND. We know the doping density of both sides of the diode. This is negative Q times NA. So we actually know the values of both of these here. We know the total charge on this side. We know the total charge on this side. The next step is figuring out the electric field. A couple things, just intuitively. Wherever you have positive charges, you have an electric field. Wherever you have negative charges, you have an electric field. You know, the electric field points away from the positive charges, and electric fields point towards negative charges. If you remember this from electrostatics. If you have positive and negative charges both, then the electric field will, if you have positive and negative charges both, then like you have here, positive charge on one side, negative charge on the other, the strongest electric field will actually be right between the two. So at x equals 0, this is where we're going to have the strongest electric field, because you have some electric field contribution from the positive charges, and you also have electric field contribution from the negative sources. So you add up the contributions of all of those, and you get the total electric field at a particular region. Now you don't need to know the details of all the superposition stuff, but you just know that there's electric field contributions from all the positive charges and contributions from the negative charges. So as a result, what happens is that, if we map out the electric field as a function of x, the electric field becomes largest right in the middle. By largest, I mean the largest magnitude. The magnitude is strongest right at x equals 0. Notice that these are all negative numbers. Okay, the electric field reaches a negative maximum here. Why is it negative?
Because the p-type is on the left and the n-type is on the right.
That's right. Another way of saying it is like the electric field is pointed from right to left. Right? Our convention is that when things are pointed from left to right, that's considered positive. If things are pointed from right to left, that's negative. Okay, so E0 is the maximum electric field that happens right in the middle of the junction. And these two equations here I'll go over in a second. Based on this charge, it turns out that based on the amount of charge density that you have, you can actually calculate what the electric field is going to be. You can calculate that the electric field will be 0 here, and it'll increase linearly by the time you get to the maximum electric field here. I'm just trying to explain like intuitively what's happening here. This is the width of the depletion region here. W going across, it's xp0 plus xn0. So let's go into more details of how you find the electric field. So with electrostatics, there's a relationship between charge, electric field, and voltage that has to do with integrations and derivatives. And I touched on this at the end of class about 10 days ago before the exam, but I think it's worth it to just touch on this again here. In physics, in high school physics, when you did something very similar to this when you covered Newton's laws of motion. Move this over here a little bit. There we go. So with Newton's laws of motion, you know, the things that you were interested in was displacement, velocity, and acceleration of the particle that you're looking at. Okay, and you saw that there were integral and derivative relationships in those situations. For example, if you knew the displacement as a function of time, if you knew w of t, then you could find the velocity by just taking dw dt. Right? So velocity is the derivative of displacement, you know, the time derivative of displacement. Similarly, if you wanted to find the acceleration of the particle, you would take the velocity and then take the derivative of the velocity to find the acceleration. Do all of you remember this from physics?
Yes.
Okay, great. If you could also go in the other direction too. If you knew the acceleration of the particle, you could take the integral of acceleration to figure out velocity, and then you could take the integral of that to find the displacement. Now keep in mind, when you did the integrals, you have to take the integral from negative infinity to time t. And you know, in some cases you have to, there were other examples that you did in physics where you had an initial condition, right? When you do an integral, sometimes you need an initial condition, right? So that's exactly the same with electrostatics. There's a similar relationship between voltage, electric field, and charge. So if you know the voltage of a system, meaning like you know the voltage of every single point in space, you can figure out the electric field by taking the derivative. And the one little point about this is that E of x is equal to negative dv dx. So there's a negative sign associated with that. Whereas when you did it in mechanics, it was just dw dt. There was no there's no sign added to it. So there's a negative dv dx. So the higher the voltage, the electric field is the gradient in voltage. Okay. You take the derivative of the electric field, you get charge. And the one little detail with that is that you take the derivative, but you also have this 1 over epsilon term here. So dE dx is equal to 1 over epsilon times the charge density. Rho here is the charge density. That's what we just looked at here. This was charge density that we were looking at. 1 over the charge density divided by epsilon is equal to dE dx, the derivative of the electric field. All right, we are going in the opposite direction. So what we have in this situation, we have the charge density. We know what the charge density is. We need to now find the electric field, and then we need to find the voltage. So we are going in this upwards direction here. In order to find the electric field with relation in terms of charge is the integral of charge. So E of x is equal to 1 over epsilon times the integral from negative infinity to x of rho of x dx. I'll talk about a little bit more about that on the next slide. But basically, it's an integral with the infinite limits of integration on the left side. You take the integral of the electric field, and you'll get voltage. There's a negative sign here, but the other parts are the same. You still have this negative infinite limit of integration here. So we'll go over that in a second. So here's how we calculate the electric field and the built-in potential. Let's just look at what's happening here. Now let me bring up my pen here. Okay. So the electric field, as shown in the previous slides, 1 over epsilon times the integral from negative infinity to x of rho of x dx. So let's piece together what this means. This means the integral, the area under the curve, of everything to the left of x. So let me show you what I mean by that. So let's say, we have this, we have a relationship for charge density here already. Now we want to find the electric field. Let's say I want to find the electric field at this point here. Okay, we don't know, we haven't created this curve yet, okay? So let's just assume that we're trying to get the electric field at this point here. So what is our equation telling us? 1 over epsilon integral from negative infinity to x of rho of x dx. What this is saying is the integral of everything to the left of x, the area under the curve of everything to the left of x. So if I look at this point x, right, I line this up here. All right, so this is my point x. So I'm told the integral is telling me to look at everything to the left of that and to find all the area under the curve of everything to the left of that. So the curve that I have looks like this. It starts here, it goes down like this, it goes up like this, and then down, and then across like this. So from this point x, if I look at everything to the left of that, what's the area under the curve? 0, right? So that's why my electric field is 0 here. I keep on going, it's going to continue to stay at 0 until I get to this point. Now let's say I'm somewhere in here. This is my x. So what I'm going to do is I'm going to look at the area under the curve of everything to the left of that. The integral from negative infinity to x of rho of x dx. So this is my rho of x dx. So the integral of everything to the left of it. So what I'm going to be looking at is the area, this area here, everything to the left of it. So that's the reason why as my point x keeps on moving, that area is going to get larger and larger. So that's why the electric field function, it just keeps on increasing like this until it gets to x equals 0 and hits a maximum. All right, and remember, this is negative area. It's area under the x-axis, so that's why it's negative, and that's why the electric field is also negative. So now my x is here, okay? So let's say I'm here. Let's just get rid of this. So now this is my point x. So the area that I'm calculating, everything to the left of x, it includes all this area here, right? So this is, I'm going to get my most negative value at this point because I've added up all the negative areas to the left of it. Everything else now is going to be positive. Once my x keeps on moving, let's say my x is here now. So now I'm going to be looking at everything to the left of x, and I'm going to get some positive area and some negative area. So the positive and negative areas are going to start to cancel one another. And so my electric field starts to decrease. By the time x gets here, now if I take everything to the left of the curve, I get this positive area, which is q plus. Oops. And I also get the negative area, q minus. We already know that q plus and q minus are equal to each other because of charge equality. So by that point, you have equal amount of positive, equal amount of negative. You sum those two up, you're going to end up getting a sum of 0. And from here on out, if you continue with x, it will stay at 0. Okay? So this idea of finding the electric field is looking at the area of everything to the left of a certain point x. All right, so I just showed you how to do that, kind of in a graphical manner. Now, if you calculate it just mathematically, let's give this a second to come back up. If you calculate it mathematically, it looks something like this. What we're doing here specifically is we are calculating E of 0. All right, so we plug in x equals 0 there. So it's going from negative xp0 to 0. Instead of having negative infinity here, we know that past XP0, there's no area under the curve, so that's why we replace negative infinity with negative XP0. And we know we have a formula for our charge density. It was already here. We saw that the negative charge density is equal to negative Q times NA. That's why we just plug that in here. And then we get a formula for our E of 0. The E of 0 is equal to Q over epsilon XP0 times the doping density NA. And from before, remember we knew that XP times NA is equal to XN times ND because of charge neutrality. So both of these equations are equivalent. You could put this in terms of NA, you could put it in terms of ND as well. All right? Now, the voltage, if we want to find the voltage, we actually have to do the same procedure again. So, let's say I want to find the voltage. Let's say I want to find the voltage at this point of x. So I have to go up and look at the electric field. The electric field plot looks like this. If I'm at this value of x, there's nothing to the left of the curve. So of course my voltage is going to be 0 there. Okay, the voltage is equal to integral of negative infinity of x, e of x dx. So I keep on going with this. You know, once I get here, let's say, at this value of x, now I'm going to start including this area of the curve. So my voltage is going to start to rise because I have a negative integral value, but I'm negating that. So my voltage starts to go up like this. It'll keep on going up because I'm getting more and more negative area as x moves across. And once I get here, the voltage stops increasing and it just flatlines at a value like this. So it's very similar to what we did with the charge density, except the shape is different now. If you want to think about this in terms of mathematically, these were, you know, the charge density plot was a constant function. You think about it. This had a constant value. It was flat like this. If you take the integral of a constant value, you get what? You get a linear function. You know, if you take the integral of, let's say, 2, the integral of 2 is like 2x, right? So that's why the electric field function is a linear function. These are lines. When you have a linear function, you take the integral of a linear function, what do you get? Quadratic, right? Quadratic. So that's why you see the electric field looks quadratic like this. It looks parabolic like at the bottom half. And then it looks like an inverse parabolic on this portion of it. So it's actually a combination of two parabolas. Because, you know, you have a line with a certain slope here, a line with a different slope here. So that's why integral of this line is parabolic. And when you start including this one, it becomes an inverse parabolic. Those details you don't need to know, but knowing the general shape here is helpful. Okay, the key thing that we are interested in as electronics designers, we are interested in V0. What is that built-in potential? Right, the built-in potential is that, like, usually it's at 0.6 or 0.7 volts, depends on the doping. So if you do this integral, you will see that the V0 comes out to W over 2 Q over epsilon XP0 times NA, W over 2 Q over epsilon XN0 times ND. So this analysis showed us that, okay, we have another formula for voltage. I just want to remind everyone that we had previously found a relationship for voltage. Let's go back up here like this. Using our energy band diagram analysis, we had found this relationship for voltage. V0 is equal to KT over Q, ln of NA/ND over Ni squared. Now we just derived a second relationship for voltage, for the built-in potential. Both are true, both are valid. So when you have, we have one formula for built-in potential, which is in terms of doping, and we have another formula for built-in potential, which is in terms of XP0 and XN0. So you can combine them and get more information about the diode. So here's just, I'll just cover these three equations and then we'll have to stop here. So you first use the charge conservation relations to get formulas relating xp0 and xn0 to the total width. So we know that this is the charge equality equation. And then this is just a definition of the width. There's a depletion width on the left side, depletion width on the right side of the junction. So by combining these, we get these relationships. Now our xp0 and xn0 is in terms of the total width, W, and the doping, Na and Nd. Second part, we plug into the formulas for VO from the last slide and solve for the width W, and we come up with this equation here. All right, and in the interest of time, I'm not going to go over the derivation of this. It's not all that important, but the result is, okay, what are we seeing here? This is actually a formula for the width of the depletion region in terms of doping. So that's important, because the width of the depletion region is an important parameter for a diode. It determines how much electric field you have and so forth. The width is a square root function of the built-in potential, V0, and it's inversely related to 1 over Na plus 1 over Nd. Now, I just want to make an important point here, is that what if we have an N-type? Let's say we have an N-type diode. Which is going to be greater, Nd or Na? Nd. So in an N-type, so in an N plus diode, guess what happens? This term actually drops out. And the properties of the N plus P diode are actually being determined by the lighter doped side, which is interesting. It's not what you'd think. You'd think that the heavier doped side determines properties. No, it's actually the lighter doped side of the diode that determines a lot of the diode properties. So in an N plus diode, this one goes away. In a P plus diode, this other term goes away. All right, the last thing I want to show here today is, let me just erase all ink here. The last thing is, using these two equations, we can also obtain an equation for xp0 and xn0 in terms of doping. Remember, xp0 and xn0 is the depletion widths on either side. So xp0 is, you're combining these two equations, and again, you get something that's a square root of V0, which is a built-in potential, and then this factor of doping. Keep in mind again that, like, if one side has much higher doping than the other, both of these equations simplify. It will simplify the math that you have to do. Okay, so basically in summary, what we did today is that we looked at the electrostatics of the depletion region. By looking at the electrostatics of the depletion region and considering these basic rules of electrostatics, we came up with a formula for the maximum electric field. So that's something I could ask you on homework. What is the maximum electric field in a diode? And you can come up with this. This is the equation that you could use to figure it. The reason why it's practically important is because a lot of breakdown effects happen at high electric fields. Okay, you want to, in designing the diode, sometimes you want to make sure that your electric field doesn't get too high. So that's why you're interested in the max electric field there. It's also relevant to things like photodiodes. The second thing we did was we came up with a second relationship for the built-in potential V0. And so now, since we had two relationships for V0, we can set them equal to one another. And that's what ultimately led to these additional formulas for things like the depletion width, the depletion widths on either side in terms of V0. So basically at this point, if I give you the doping of a diode, you should be able to first figure out the built-in potential. It's very, very straightforward. And then from there, you should also be able to figure out the depletion widths. Okay? So if you're able to, at home, I suggest just doing this problem. We have a step p-n junction with doping on either side. So figure out the built-in potential and then also draw plots of the charge density, electric field, and voltage. This is something you can do at home, very similar to what we did in class today. Great review, great way to review the concepts. Okay, thanks for staying with me a few minutes later today. Really appreciate it. So Wednesday, please do make sure that you've had, you have your topic selected. Send me a one-paragraph summary of what you're going to be working on. If you want some feedback on it, send it tonight or early tomorrow. I can send you some feedback on it in case you need to switch topics. Otherwise, like on Wednesday, you can just submit your topic. Just send it by if you can post it on Blackboard. I'll try to set up something with that. If I have any issues with it, then just email it to
So
me.
do we just need one person just from our group to?
Yeah. I think on not Blackboard, but Canvas, you can indicate one person as your group leader, and that person can submit. All right. Thanks, everyone.